Hello again, Math 10Cs. In today's lesson, we're going to wrap up this really short unit of study on characteristics of linear relations. And the way we're going to do that is we're going to compare the slopes of line segments that are parallel and compare the slopes of different line segments that are perpendicular. However, before jumping into that comparison, we need to review a little bit about some transformations that you would have covered in some previous math courses. I know I teach this in grade 7 science as like one of the very first units of study, where we take points or we take shapes and we translate them along straight lines. We reflect them about lines of reflection, or we rotate them about a point called a center of rotation. We're only going to have to worry about two of those transformations here. One, which is a translation, which is actually really simple to do. And then secondly, a rotation. And rotations are actually quite a bit more complicated to do compared to a translation or even a reflection. Okay, so let's start off with the easy part, which is going to be a translation. So we're going to begin by just plotting the point A, 2, 5 on this grid. So 2, 5 would be 2 to the right, and it would be 5 up. So that point's going to be located right here. So we'll call that point A. Now, a translation 3 units to the right and 2 units up would be take that point and move it 1, 2, 3 to the right, and then move it 2 units up, 1, 2, up. And then this point is what we call the image of this point or this object. And the problem here wants me to label it as point B. So point B would have coordinates of 5, 7. Okay, so all I've done is, I moved it towards the right and then up, but ultimately I just slid it along a straight line. That's what that translation is. Now, rotation's quite a bit more difficult to do. When I actually teach this in class to my grade 7s, I use a trick involving a piece of overhead transparency, which actually makes the translation quite easy to do. Now, unfortunately, I don't have the ability to show that in the in this Smart Notebook file. So I'm going to use a bit more of a roundabout way to do the rotation. Now, if you find this confusing, it's not a big deal. You're not going to actually be expected to rotate shapes at any point. But I just want to show you how I actually get the rotated point. So what we want to do is we want to take this guy and we want to rotate it 90 degrees clockwise about the origin. Okay, so I'm going to label another point at the origin, which I'm going to call point Z. Point Z is what we call the center of rotation. So we're going to rotate point A about that point, and we're going to do it by 90 degrees. The first thing I'm going to do is I'm going to make a line that connects the center of rotation to point A. So I'll pick a line here, and I'm going to make it a different color. So let's make it purple in color. And then I'm just going to make it a dashed line, and I'm going to connect this line. Let's see, is this the correct line here? Yes, okay. I'm going to connect this line from the center of rotation to that point, okay? Now, to rotate this guy by 90 degrees, we want to use a geometric tool that actually has angles labeled on it. So I'm going to grab a protractor. Okay, here's my protractor. And we can make it a bit smaller. Okay, I'm going to take the protractor, and what I'm going to do is I'm going to take the center of the protractor and put it at the center of rotation. Okay, so it's on the center of rotation of the graph here. Then I'm going to take the protractor and rotate it, and I'm going to rotate it in a way so the base of the protractor lines up with that line that connects the center of rotation to the point I'm interested in. Okay, so I now have my protractor, which is going to be lined up. The center is at the center. The center of the protractor is the center of rotation, and I have the base of the protractor lined up with this line that connects the center of rotation to the point that I'm going to rotate. Now, to rotate this point here, we're going to rotate it by an angle of 90 degrees. We can start counting. So we can rotate it from 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. Now, what this means is that this rotated point is going to lie somewhere along a line that connects the center of rotation to 90 degrees on the protractor. So let's see if I can actually like get that line here. Okay, so I'm just going to take this line and see if I can move it. Okay, and I want this line to go along 90 degrees. So I'm going to change this a little bit, this angle. Okay, let's see, can I get it to line up with 90? Almost got it. Maybe just a little bit more of an adjustment. Okay, that's pretty good. Okay, so we're going to take this point and we're going to rotate it from here somewhere along this line. Somewhere along this line would be a rotation of 90 degrees. Now, to visualize what the rotation would look like, we can actually use another geometric tool. Again, like I said, this is a really complicated way to do this without like a transparency. And I'm going to pull out a compass. Okay, I'm going to take the compass and I'm going to put the center of the compass at the center of rotation. So that's going to be right here. And then I'm going to put the pencil edge of the compass at the location of this point that I'm going to rotate. Okay, so let's try to get it at that point. Okay, it looks pretty good. Yeah, yeah, I'd say that's pretty good. Okay, now what I'm going to do is I'm going to take the protractor and I'm going to rotate it, and I'm going to stop rotating when I get along this line that's 90 degrees. So if I do that, it's going to stop about right here. Okay. Now that point, okay, and we'll label it on the grid in a second here. That point looks like it has coordinates of 5, -2. So we'll go back to my pen and I'll just label this. So this would have coordinates of 5, -2. Okay, let's pull all this junk off of here just for a moment, and then we'll label the point. So put the protractor, the compass here, protractor over there, and then let's label this point C. So this point C would then be located right here. Okay, that's where my point C is located. That's a 90-degree rotation of that point in the clockwise direction. Now C wants me to do it in the reverse direction. Okay, so the reverse direction. So let's take our protractor again. Now we're going to rotate the protractor in a different direction. So we'll take the protractor and let's spin it around. And I want the center of the protractor to be the center of rotation. And I want the base of the protractor to line up with that line again. So that's going to be at this location. Okay, now 90 degrees in the other direction is going to involve, let's count again. So we go 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So it's going to be a line that is going to, it's going to be a line that falls along 90 degrees right here. Now, it turns out that this line that connects Z to point C, I can actually just extend it and it would actually give me a line that's along the 90 degrees. So I'm going to try to take this line and see if I can extend it. Okay, make sure it's along the protractor here. Okay, so around 90 degrees. Okay, so when I rotate this point A by 90 degrees counterclockwise, it's going to fall somewhere along that line. And now I can use the compass to determine where that point is. So we'll go over here and we'll put the kind of like the sharp edge of the compass at the center of rotation. Take this guy, and then I'm going to have the pencil part of the compass on the edge here, where it's lining up with the, again, where the pencil edge is on the point I'm going to rotate. And then I simply just going to take this guy, and it's kind of falling out of the window. Take this guy and then rotate it, which I can't seem to do because it's just out of range. Shoot, yeah. Okay. I'm gonna start to rotate it a little bit. So let's just get it lined up, and I'll rotate it a bit off screen here. Okay, so let's start to rotate it a bit, just so I can actually see the thing I can rotate. I need that green circle to be able to rotate it. Okay, so I've started to rotate it, and now I'm going to stop the rotation when I get towards the line where this would be 90 degrees. Okay, so that's about this point here. So if I label that point, it looks like that point is -5, 2. So you have -5, 2 is that point. And then let's get rid of all this stuff now. So we don't really need this anymore. So let's see if I can delete it. Okay, so get rid of it. Let's take this guy, same thing. Let's try to get rid of it. Delete it. Okay, and then we'll just label this point on the grid. So this point on the grid would be located at -5, 2, which is going to be located right here. So that would be point D. And that's a 90-degree rotation of that point A, about the center of rotation in the clockwise direction. Okay, that was a really long roundabout way to actually do a rotation. Again, there's simpler ways to do it, but I just wanted you to have like some kind of visualization as to how I did this. Although you're actually not going to be required to do this in any of the homework problems. Okay, so the first thing we're going to do is we're going to investigate what happens if you have line segments that are parallel. Okay, so it says on the grid shown, the grid shows the image of line segment AB after the following transformations. So it says a translation 4 units right and 1 unit down to form line segment CD. Okay, so let's try to form line segment CD starting from AB. Okay, so let's go to my pen here. Okay, so we're going to go 4 units to the right and 1 unit down. So let's start with the end point. So we go 1, 2, 3, 4 units to the right, and then 1 unit down. So my point's going to be located right here. Okay, we're going to call that point C. And then take this endpoint and go 4 units to the right and 1 unit down. So 1, 2, 3, 4. 1 unit down will be located at this position. So that's going to be point D. And then we're just going to connect the dots. So I'll take a line. Let's go to a solid line now. And yeah, I'll just make this guy red in color. And then connect the dots. And then let's do a line segment from here to here. Okay, and then we also want to do a translation of 3 units left and then 6 units up. So I'll go to a different color. Let's do green this time around. Okay, so we're going to go from point A, we're going to go 3 left and 6 up. So we're going to go 1, 2, 3, and then 1, 2, 3, 4, 5, and 6. So point E is going to be located all the way at the top here. Point F, I'd form by taking the vertex B and doing that translation. So 3 left, 6 up, 1, 2, 3, and then 1, 2, 3, 4, 5, and then 6 would be located at this position. Okay, so that's going to be point F. And then let's just draw that line. Make sure I got the right color. Okay, and let's go from point E to point F here. And then we're good. Okay, and the final one says do a translation of just 3 units down. So we'll do this line in blue. Okay, so we take each of these points and just go 3 units down. So 1, 2, 3. So this would give me line segment G. And then 1, 2, 3 would give me a line segment H. Then we'll just connect those lines. Make sure we got a blue color here, good. Okay, connect the lines. And, oh, that was not a line. So let's just delete that. Okay, line, I want to be here, okay. So G to H. Okay, now it says, calculate the slope for each of the line segments. Now, if you look at the graph here and you look at all 4 of those line segments, what can you tell me about all those line segments? Well, you should be able to tell me that they are all parallel to each other, okay? Parallel because each line segment would be the same distance apart, and it doesn't matter how far you go along the line segment, they do not get closer together. So I could actually like illustrate that on the graph here. So let's just pick purple as a pen color. Okay, and again, those to indicate that things are parallel, you can use these little arrows. Okay, so we could put like a little arrow here, a little arrow right here, a little arrow right here, and then a little arrow right there. Okay, so all of these guys are parallel to each other. So let's calculate the slope of one of these guys, because that's all we're going to need to do. So let's do it for a line segment EF here. Okay, so let's draw our slope triangle. So our slope triangle would, we go down, and then we go across. And let's calculate the rise and the run. Okay, so the rise here would be equal to, well, from E to F, you're dropping by 3, so that'd be -3. And then from E to F, you're going across by 1, 2, 3, 4, 5, 6. So if I calculate the slope, and this is actually going to be the slope for all line segments, for all of these lines. Again, we use the variable m to represent the slope, so we can say m of line segment EF would be equal to rise over run, which would be equal to the rise is -3, the run is +6, and the fraction -3 over 6, if you divide both the top and bottom by 3, would give you 1/2, or -1/2 because the top number is negative. Okay, it says the 4 line segments are parallel. Make a conjecture about the slopes of the parallel line segments. Well, if you look here, the steepness of every single one of these line segments, whether it's EF, CD, AB, or GH, they are all the same. Okay. Therefore, if you have line segments that are parallel, we can say the slopes of parallel line segments are the same. Therefore, if the slope of like line segment EF is -1/2, then I can say that m of line segment CD is equal to m of line segment AB is equal to the slope of line segment GH, which is equal to the slope of line segment EF. If your line segments are all parallel to each other, parallel line segments would all have the exact same slope. So that'd be -1/2. Okay, that's a pretty intuitive result, I think. If line segments are parallel, the only possible way they could be parallel is if the steepness of every single line was going to be identical. Because if they weren't, then there would be, the lines might intersect at some point. Okay, so that's parallel line segments. Now, perpendicular is a little bit tougher. So we're going to investigate perpendicular line segments. All right, so it says, first of all, on the grid below, plot the point 5, 2. Okay, so 5, 2 is going to be 5 to the right and 2 up. So that's going to be located here. So I'm going to label that as point A. And it says draw a line connecting the origin to that point. Okay, that's because we're going to treat the origin as what we call the center of rotation in a second. Okay, so we'll do a line that connects it. And just like on the previous page, I'll do it with a dashed line. So let's go with red here. And yeah, line segment. No, I'm not on line. Here we go. Line segment, red, dashed line. Okay, let's draw this now. Okay, so let's connect these points here. Okay, so I plotted that point and I drew a point that connects that point to the center of rotation. Okay, what we want to do is we're going to rotate this guy by 90 degrees clockwise and show where it is on the graph. Okay, so once again, I can do all this like work with like the protractor and the compass to show it. So let's pull the protractor on here. Okay, so what I'm going to do is I'm going to take the protractor and let's see if I can make it smaller first. Okay, yeah. Okay, take the protractor, put the center of the protractor at the center of rotation, and then I'm going to get this guy to line up so that the base of the protractor falls on this line that is going to connect the center of rotation to the point I'm going to rotate. Now, we're going to rotate this guy by 90 degrees clockwise, so this point of rotation is going to fall somewhere along a line that would be like 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So I'm going to draw a line that just connects the center rotation to like where 90 degrees in the protractor would be. Okay, so maybe this would be, let's see how close I can get this. This would be a line that might look like, okay, we've got to move it a bit. Okay, not quite there. So let's take the line, just adjust it a bit. Okay, so the center, the rotated point is going to be somewhere along that line because that'd be a 90-degree clockwise rotation on the protractor. So we'll take the compass now. Take the compass. Okay, put the pointy edge of the compass on the on that bottom part there. If you can shrink the compass, I don't worry about it. Okay, and then I'm going to take this guy and let's rotate this thing a little bit. I have to get it so it's the pencil edge is going to be on point A. Okay, so I'm not quite there. Let's get a little bit closer. Not quite again. Okay, pretty close. Rotate just a little bit and see if I can get it. Okay, so that's roughly about the point. Okay, now we're going to take this compass and we're gonna rotate it by 90 degrees. So we're gonna stop when we hit that line. Thanks very much, everybody. Bye. Okay. Sorry about that interruption. Someone came on the announcement there. Okay, so we're going to rotate this guy. Let's see if I can actually. Okay, good. I can just fit it in. Okay, so again, we're going to start here. Okay, and we're going to rotate it and stop when it actually gets to this graph. Okay, now this is roughly at the point 2, -5. It would hit at about that grid line intersection point. So let's write that point down. Rotate the line, and we're going to get a line that is going to be at about 2, -5. Okay, so let's erase all of this and then get rid of these the protractor and the compass. We don't need them anymore. Okay, get rid of these. Delete. Okay, and let's relabel this point now. So let's make it in blue. So you got 2, -5. So that's going to be at about this location. Okay. So that's going to be my rotated point. Let's call that point B. Okay, so if you take point A and rotate it 90 degrees clockwise in the grid, that's where that point would be. Okay, now it wants me to calculate the slopes of these two lines. Okay, so we're going to draw some slope triangles to do this. So the slope of the line connecting Z to A. So we're going to focus on this line segment. Okay, so here's the base of the slope triangle, and here's the height of the slope triangle. So my run would be equal to 5, and my rise would be equal to, it goes up by 2, so it would be positive 2. And then, so we can calculate that. So we'll say the slope of line segment so it goes from points, the slope of line segment ZA. So we'll say ZA would be equal to rise over run which would be equal to positive 2 over 5. Okay, now let's connect a line from Z to B and calculate the slope of that line. So we'll do purple here. Okay, so slope triangle, go down here, cross there. Okay, so the run would just be a cross by 2. And the rise would be, well, from Z to B, you're actually going down. You're going down by 1, 2, 3, 4, 5. So this would be negative 5. So your slope of Z to B would be equal to rise over run. And that would be equal to negative 5 over 2. Now, just for a brief moment, just look at this. So these two line segments, Z to A and Z to B, they are perpendicular to each other. Okay, there'll be a 90-degree angle between the two. So look at the two fractions here and try to identify what's the connection or the relationship between two line segments that are perpendicular. And I'll address this in a moment. What it says now, though, is multiply these two slopes together. Okay, so let's go ahead and do that. So let's go down a bit. So if you multiply these two slopes together, you would get 2 over 5 multiplied by negative 5 over 2. This would be equal to negative 10 over 10, which would turn into negative 1. Okay, now it says repeat this for another point on the grid. No, I don't think we need to do that. It's again, like it's just so tedious with the smart tools to actually show the rotation point. So this will be good enough in comparing. Okay, so what we want to look at here is how do the slopes of line segments that are perpendicular compare to each other? Now, if you take a fraction and you multiply by another one and it's equal to 1, we refer to that as the reciprocal of the fraction. So the slope of line segments that are perpendicular, yes, there's a reciprocal involved because the reciprocal of 2 over 5 would be 5 over 2. However, it's not just going to be the reciprocal of like the slope, it's actually going to be the negative reciprocal of the slope. So any two line segments that are perpendicular would have slopes that are both a reciprocal and slopes that are negative of each other. Okay, so for part C, it says make a conjecture about the actual slopes. Okay, so what I can say here is that, let's do this in blue. Okay, perpendicular slopes or perpendicular line segments have slopes that are the negative reciprocal of one another. Okay, so that is like the key defining a relationship between line segments that are perpendicular. Perpendicular line segments have slopes that are a negative reciprocal of each other. And I proved that by using this example up here. Because I had a line segment of this first line is 2 over 5, Then we rotated that line segment 90 degrees so it's perpendicular, and then we got a slope that was a negative reciprocal. Okay, now we're going to generalize this a little bit. So it says complete the following to prove the conjecture in C. It says under rotation of 90 degrees clockwise about the point P. So the point P has just generic coordinates A and B, and we're going to turn it into point Q, which would have coordinates of B and negative A. Okay, so if we calculate the slope here, so YP minus YO, so it wants me to calculate these slopes. So this time around, we're actually using the, so they're labeling the center rotation as point O, which should have coordinates of 0, 0. So here, to figure out the slope using that endpoint formula, it'd be YP minus YO. The Y coordinate of point P is B here. The Y coordinate of point O is 0, so you'd have B minus 0, which is B. XP minus XO. The X coordinate of point P is A, and the X coordinate of point O is 0, so this would just be B over A. And if we look at this point, so we go YQ minus YO. Well, the Y coordinate of point Q is negative A. The Y coordinate of point O is 0, so this would be negative A. And then XQ minus XO, the X coordinate of point Q is B, and then the X coordinate of point O would just be 0. So that'd be B minus 0, which is B. So if you look right here, we're just writing these in terms of variables, in terms of instead of actual like numbers. So the reciprocal of the fraction B over A would be A over B. But perpendicular line segments have a slope that is a negative reciprocal. So if you actually take the slope of two line segments that are perpendicular and multiply them together, so if we want the slope of line segment OP multiplied by the slope of line segment OQ, this would be B over A times negative A over B would be equal to negative AB divided by AB. And then these numbers just cancel each other off, or values cancel each other off. AB divided by AB would cancel off, and this would just leave you with a slope that is negative 1. So if you actually take the slope of two line segments that are perpendicular and multiply them together, you'll get a value that's equal to negative 1. And that's because the slopes of perpendicular line segments are negative reciprocals. Okay, let's go to the next page. Okay, so this is a review. This just summarizes everything we just derived on the previous pages. So it says, consider two lines with a slope M1 and M2. Lines are parallel if they have the exact same slope, okay? Parallel if they have the exact same slope. And again, we showed this on the first page, okay? We showed this down here. If all these line segments are parallel, they would all have the exact same steepness, okay? So we proved that. Line segments that are perpendicular, if you take the slopes and multiply them together, the product of the slopes would be equal to 1. Although this is usually the way I memorize it, for perpendicular lines, the slopes are negative reciprocals of each other. And that's what we saw in the previous example here, okay? The slope of this segment is 2 over 5. The negative reciprocal of a perpendicular line segment has a slope that is negative 5 over 2. Okay, so let's start to make use of this now. Okay, so it says, consider line segment AC, which has a slope which is 3 over 4. Write the slope of the line segment GH, which is parallel to AC. Well, we know the slope of AC is equal to 3 over 4. If AC is parallel to GH, then we can just write down, so I can say if AC, we can use these little lines here. This means like if they're parallel, two like lines just like side by side. If they're parallel to each other, then it would just be the same slope. So the line segment of GH would just be equal to the same thing. It would also be equal to 3 over 4. It says write the slope of line segment BH if it's perpendicular to AC. Okay, so AC, would have a slope of 3 over 4. Now, if AC is perpendicular, so perpendicular, we can use this symbol, just draw two lines that intersect at roughly a 90-degree angle. We use a square to represent that. So if that's perpendicular to BF, then how are the slopes related? Well, the slope of line segment BF would be the negative reciprocal. So this is a positive number, so it becomes a negative number then. The reciprocal of this fraction would just be negative 4 over 3. Again, if you're ever not sure if you did that correctly, take the two perpendicular slopes, multiply them together, and they must give you a number that's equal to negative 1. Okay, second example, it says the slopes of two line segments are given. Determine if they are parallel, perpendicular, or neither. Okay, so M1 has a slope of 1/4. M2 has a slope of 3 over 12. Well, if you divide these two, the top and the bottom, by 3, this would give you 1/4. Okay? If M1 is equal to M2, it means that they're parallel line segments. Okay? Parallel lines. Okay, this one, you have M1 is 5 over 7. M2 is 14 over 10. Okay, let's try to reduce that fraction to see if we can compare the slopes. So if we divide by 2, this would be equal to 7 over 5. Now, at first glance, you might be like, oh, these guys are perpendicular because this slope is the reciprocal of the other one. But it's not just a reciprocal, it must be a negative reciprocal. So I could say here, the negative reciprocal is negative 7 over 5. So in this case right here, how would these two lines compare? Well, they'd be neither perpendicular or parallel. So I can say neither parallel or perpendicular. Okay. If this guy was negative 7 over 5, then it would be perpendicular, but it's not. Okay. Example 3 says if point P and if point P is the point 4, 7, Q is the point 6, negative 2, find the slope of a line segment that is parallel to line segment PQ and perpendicular to line segment PQ. Now, the first thing we need to do is, if we want to know what the slope of these line segments are, we need to figure out what the slope of a line segment joining P to Q is. So let's figure out that first. Okay, so we want to figure out the slope of a line segment PQ. So that could be YQ minus YP using the slope formula with the 2 points on the line over XQ minus XP. Okay, let's plug these numbers in. So YQ is the Y coordinate of point Q, which is negative 2. Subtract YP, which is the Y coordinate of point P, which is 7. Divide this by the X coordinate of point Q is 6. Subtract the X coordinate of point P is 4. So this would be equal to negative 2 minus 7 is negative 9. And then 6 minus 4 would just be 2. Okay, so we want to know the slope of a line segment that's parallel to this guy. Well, line segments that are parallel just have the same slope. So if MPQ is equal to negative 9 over 2, then the slope of a line that is parallel to line segment PQ would just have the same slope. B, what's the slope of a line segment that's perpendicular to this one? Okay, so the slope of line segment PQ is negative 9 over 2. And the slope of a line segment that is perpendicular is a negative reciprocal. Okay, so first of all, if we take the negative reciprocal of a negative number, that actually gives me a positive value. And we flip the numerator and denominator, and we get 2/9. Okay, so -9/2, the negative reciprocal of that would be 2/9. And again, if you're not sure, you can always take these these slopes, multiply them together, and see if you get a value that's equal to -1. Okay, last page. All right, it says here, you have triangle LMN has coordinates of -4, 2, -2, 7, n is 1, 0. It says use slopes to show the triangle is right angled at L. Well, I'm just going to draw a picture so we can visualize this a bit more. Now, I'm going to go back to the first slide of the note just because it actually does have a grid in which we could plot these points on. So let's go all the way back to just the first slide. And I'm just going to delete all these things here. Okay, so let's get rid of those. Let's take these lines and let's get rid of them. Take that line, delete it. Okay, so I'm going to plot these points. So the points, it tells me that point L has coordinates of -4, 2. So that'd be 4 to the left and 2 up. So that'd be located here. And then it says point M has coordinates of -2, 7. So 2 to the left and 7 up would be located up here. So that'd be point M. And then point N has coordinates of 1, 0. So that would just be 1 to the right, and you just stay on the x-axis. Okay, so what the question wants us to do is it's asking us, so let's just connect these, let's connect the lines here. Pick a color, blue. Okay. So let's connect a line from M to L and connect a line from L to N. And then what it wants us to do is it wants us to determine if the line segments ML is perpendicular to LN, because the question we're trying to ask right here is we want to know, is angle L perpendicular? Or is angle L equal to 90 degrees? Now, the way we're going to prove this is we're going to calculate the slope of line segment ML. We're going to calculate the slope of line segment LN. Okay, so we're going to, sorry about that interruption again. We're going to calculate the slope of line segment ML. We're going to calculate the slope of line segment LN, and we're going to see if they're perpendicular to each other. If they're perpendicular to each other, this angle L here would then be equal to 90 degrees. Okay, so let's go back to that page with that example on it. Okay, so let's figure out the slope of line segment L to M. So we'll do M, L, M is equal to, I think we were doing LM. Which one are we going to start with here? Yeah, let's go L to M first. We'll go L to M, and then we'll figure out the slope of line segment L to N. Okay, so this would be YL, sorry, let's do YM minus YL. Doesn't matter what order you do it again. Divided by XM minus XL. So this would be equal to the Y coordinate of point M is 7. Subtract the Y coordinate of point L is 2. So you have 7 minus 2. Divide by XM is -2. Subtract the X coordinate of point L is -4. 7 minus 2 is 5. -2 minus -4 would be -2 plus +4. So that would be 5/2. Okay, we're also going to figure out the line segment of L to N. Okay, so that would be YN minus YL over XN minus XL. So this would be equal to point N as a Y coordinate of 0, point L as a Y coordinate of 2, and then XN, X coordinate of point N has an X coordinate of 1. Subtract the X coordinate of L, which is negative 4. So 0 minus 2 is negative 2. And then 1 subtract negative 4 would be adding a positive, so that'd be 2 over 5. Okay, and what I can notice immediately is that the slope, LMN, is the negative reciprocal of MLN. Therefore, this tells me that MLN, or actually this changes, we'll say that line segment, so LM, is then perpendicular because the slopes are negative reciprocals, so those are LM be perpendicular to LN, and yes, that angle L is actually a 90-degree angle, okay? So we proved that just by showing that the slopes of the two line segments are perpendicular, and we knew that because they're negative reciprocals of each other. Okay, one more. It says two lines have slopes of negative 3 over 4 and k over 5 respectively. Find the value of k if the lines are parallel or if the lines are perpendicular. Okay, so let's label these. We're going to call this guy slope 1, and we're going to call this one slope 2. Now, if two line segments are parallel, they have the exact same slope. So that would tell you that M1 is equal to M2. Therefore, we can write this as a slope of M1 would be, let's put the negative at the top of the fraction. So you have negative 3 over 4 would be equal to k over 5. Negative 3 over 4 is a slope of slope M1. K over 5 is a slope M2. We've got to figure out what the value of k is. To do this, we can do some cross multiplication. So we got to isolate for k. To get k isolated, just bring this 5 up and across to this side. Therefore, you would have k would then be equal to, if you bring this guy up, you got to multiply it. So it'd be negative 3 multiplied by 5, and we're going to divide that by 4. Negative 3 times 5 is negative 15, and then divide that by 4. So you'd have your k value would be equal to negative 15 over 4. Now, if two slopes are perpendicular, it means that the one slope has a negative reciprocal of another one. Now, the other thing I said you can do is if you want to test to make sure they're negative reciprocals, if you take the slope of one of them and multiply by the slope of the other one, it must be equal to negative 1, okay? So let's plug these in. So M1 is negative 3 over 4, multiplied by M2 is k over 5, and that must be equal to negative 1, because if you take the slope of this guy and multiply by a perpendicular slope, it has to give you negative 1. That tells you that they're negative reciprocals of one another. Okay, let's simplify the left-hand side of the equation. So negative 3 times k would just be negative 3k. And then 4 times 5 would be 20. And this would be equal to negative 1. Now, we need to isolate for the value of k. So first of all, let's get the negative 3k isolated. So we'll do that by cross-multiplying, bring this guy up to the other side. So if we do that, this would then be negative 3k would be equal to -1 multiplied by 20. So this would then be -3k is equal to -20. And then to get k by itself, divide by 3, which will cancel off that -3. Divide by -3. The fraction 20 over 3 does not reduce, but negative divided by a negative is a positive. So in order for those slopes to be perpendicular, the value of k would need to be equal to 20 over 3. Sorry, a bit of a long lesson. I think it would have been a lot shorter if I could have shown the overhead transparency trick compared to like doing like the really long roundabout way with the protractor and the compass. But anyways, you guys can do questions numbers 3, and then 6 through 11. And then I'll talk to you in the next set of lecture videos, which is going to start the following unit on, again, we're going to stick with dealing with linear relations, but we're going to focus more on the equations that define a linear relation then. And I'll talk to you then.